Thank you for having me in this symposium. Thanks everyone for coming. Today, I'm super excited to share my PhD work that I did together with Mike May, Bruce Ranalla, and Brian Moore on reviewing the impacts of model misspecification on inferences of disease spread and the solutions to alleviate these impacts. Phylogenetic methods have been used extensively to address important questions about pathogen spread. For example, you may want to ask, what were the major routes of SARS-CoV-2 dispersal among European countries? Or when was SARS-CoV-2 first introduced into the United States? To answer those questions, we collect viral sequences from different geographic areas through time. Imagine now we have a simple case where there are three geographic areas to consider: the United States, Europe, and China. After obtaining the sequence data, we first infer data phylogeny, where each tip is a viral sequence sampled from one of the geographic areas at a given time. Here, because the viral sequences were sampled continually through time, we can see that many tips of this time tree are like fossils. Similar to the substitution process, we imagine that the discrete geographic area evolves over the tree under a continuous time Markov chain, the CTMC, where an instantaneous read matrix Q is used to characterize the process. Here, I illustrate the Q matrix as a map, where an arrow from area I to J represents a dispersal route from I to J, whose thickness indicates the relative dispersal rate over the route. So this map shows a single dispersal route from China to Europe. Then let's add another one from China to the United States. Note that if the virus originated in China, this is the minimally connected case that would allow the virus to disperse to all the three observed areas. Then the model can be more complex with more and more dispersal routes. In a pre-pandemic world, we should expect most, if not all, dispersal routes to exist. However, when there is a travel ban between China and the United States, dispersal cannot occur directly between those two areas. The corresponding dispersal routes are thus removed from the model. These pairwise dispersal rates are relative, and the model contains another independent parameter mu that represents the average rate of dispersal among all areas. So we imagine the virus originating in one of the areas at the root of this tree, then evolve over the tree under the geographic model, giving rise to the areas we observe at the tip. A version of this model was implemented in a popular phylogenetic program, BEAST, that has been applied in many empirical studies, including the one studying SARS-CoV-2 dispersal. The parameters of this model are estimated in a Bayesian framework. Specifically, we compute the posterior probability of these parameters as the product of the likelihood and the prior divided by the marginal likelihood. Conceptually, the prior reflects our beliefs about the parameters before looking at the data, and it will be updated by the information in the data via the likelihood function to produce the posterior, which reflects our belief after observing the data that we will draw our conclusions upon. Typically, in Bayesian inference, we expect the data to contain much more information than the prior, like when inferring a phylogeny using genome alignment, in which case what exactly our prior belief is shouldn't matter. Conversely, with very limited data, such as a single geographic site, we are naturally concerned that the posterior of the dispersal parameters may be sensitive to the prior choice, as shown in the top graph. This prior sensitivity issue is further exacerbated by the complexity of the geographic model. To illustrate this, let's look at the model again. Here shows an asymmetric geographic model, meaning that the forward and backward dispersal rates can be different. The dispersal matrix can also be symmetric, where the forward and backward rates are assumed to be always identical. So in this symmetric model, when there are three geographic areas, the only three parameters need to be estimated, right? Quite simple. While in reality, we have desire to include more areas so that we can understand the dispersal dynamics better, and we can see the number of parameters scales geometrically with the number of areas. But the data are still limited to this single geographic observation for each sequence, raising our concern about the ability to estimate these many parameters. And this is not just a hypothetical case, as many of the empirical studies include more than 10 or even 20 areas. So let's look at how are the priors usually specified. Recall this method is implemented in the program BEAST, which provides a helper program Beauty as an accessible way to specify model and priors that most people use to set up their analysis. Therefore, among the increasing number of empirical studies using this method, 93% of them have chosen the default priors recommended by Beauty. Let's take a closer look to see what are these default priors. First is the prior on the number of dispersal route delta This default prior centers on the minimally connected case, while the prior probability on intermediate number of dispersal routes are thus very close to zero under this default prior. In reality, we usually expect viral dispersal dynamics to be much more complex than the minimal connected case, so this default prior seems quite counterintuitive. In the experiment below, we specify an alternative prior that centers on intermediate number of dispersal routes. More importantly, this alternative prior is also much more diffuse across all possible delta. Next, let's look at the prior on another focal parameter, the average dispersal rate mu. Recall that mu indicates the expected number of dispersal events in one time unit. So the prior on mu represents our belief about the parameter of dispersal, about the number of dispersal events over the entire dispersal history. Under the default prior, it is very unlikely for there to be more than a handful of dispersal events over the entire history, no matter how many sequences there are or errors there are in the dataset or how long the dispersal history is, which again seems quite counterintuitive. In the experiment below, we specify a more diffuse alternative prior on mu, where the expected number of dispersal events naturally scales with the duration of dispersal history, shown by the blue bars. So the default priors on both focal parameters are strongly informative and biologically unreasonable. But does that really matter? Let's look at their empirical impacts. Here we collected 14 datasets from 8 published studies, shown as the orange dots in the scatter plot, attempting to represent different variances as well as number of errors and the number of tips. We analyzed each dataset under a suite of geographic models, including all combinations of default and alternative priors on the average dispersal rate mu, the default and alternative priors on the number of dispersal routes delta, and whether the Q matrix is symmetric or asymmetric, resulting in these 8 model combinations. First, we'll compare these competing models using Bayes factor. Here's the log Bayes factor table. They're on log scale, so the more negative it is, the worse the model. Each row here represents an empirical dataset, and each column corresponds to a candidate model, showing the Bayes factor comparing the model in that column to the best model, which is marked by the blue background cell. We can see that the model with both default priors referred to as the default prior models are the worst model, while the models with both alternative priors, the alternative prior model are the best model. This pattern is pervasive across all the dataset, demonstrating our concern that the default priors represent biologically unrealistic belief about the true dispersal process. We also assess the absolute fit of the prior model to the data using posterior predictive simulation. Here's a table showing the posterior predictive p-values. The p-values are colored in red here indicate the model cannot adequately describe the data. And we can see the default prior model is always inadequate, whereas alternative prior model is always adequate. The default prior model fit the data really poorly. But do the prior model also affect parameter estimates? Let's look at some examples comparing the default and alternative priors. First, let's look at the impact on ancestral area estimates. When the first community COVID-19 transmission was detected in the United States, there were 2 competing narratives. Either it was seeded by someone from California or British Columbia to Washington, or it was seeded directly by a traveler flew from China. This question can be addressed by estimating the ancestral areas of the sequences in the Washington clade. Here's the result. The size of each slice in the pie chart indicates the posterior probability of a given area to be the source of the epidemic. Under the default prior model, the virus is inferred to be introduced from other Western North American areas with an overwhelming probability shown by the very large blue slice. However, under an alternative prior model, the probability that it was introduced from West North America shrinks dramatically and becomes equivocal with the probability that it was introduced from a sub-area of China. This impact is prevalent across our dataset, meaning that we would frequently infer a different, likely wrong area as the source of the epidemic under a default prior. Empirical studies also focus on the inferred number of pairwise dispersal events to identify the source sync dispersal dynamics. For example, we may want to know which preceding area was the major source of domestic dispersal during the early phase of the COVID-19 pandemic. To answer that question, we can look at the percentage of domestic dispersal events originating from each Brazilian area, and here's the result. Each bar here indicates the estimated percentage. The orange bars currently showing are the estimates under the default prior model. And we can see that Sao Paulo is inferred to be the only major source we see in Brazil, as 85% of domestic dispersal events originated from there. Now let's look at the result under the alternative prior model shown by the blue bar below the axis. Now Sao Paulo is inferred to contribute only less than 20% of the domestic dispersal events, while 5 other areas each contributes about 10%. Therefore, these two models reveal very different dispersal history and indicate distinct intervention strategies. The default prior model tells us that we should put most of our efforts in containing the spread of the virus off Sao Paulo, whereas the alternative prior model says that the effort should be spent more or less evenly on mitigating the spread of the virus between major cities in Brazil. Again, this impact is pervasive across all data sets. So the prior choice really matters in these inferences, and the default prior model produced qualitatively different and likely problematic results. These findings so far have been a little bit pessimistic. So to turn it in a more positive way, we develop an interactive utility called priority tree, which allows people to specify their priors and assess prior impacts more easily. Specifically, priority tree allows users to interactively adjust the prior distribution. And all the other displays, as you can see here, including the method description, analysis script, change accordingly to user specification on the fly. Priority tree also help users set up BIS analysis that assess prior impacts, following the approach I took in this study, including robust Bayesian inference, marginal likelihood estimation, data cloning analysis, as well as posterior predictive checking. It also provides functionality to summarize this analysis as figures or tables. At the end, it even writes a method section for you according to your specification, intending to facilitate explicit communication of prior usages and make the studies more reproducible. With that, I would like to thank many people help me with this project, my collaborators, especially my PhD advisors, Brian and Bruce, my funding sources, and you all for listening to this talk. This work have been published earlier this year, so if you're interested, please check them out. And I'm more than happy to take any questions now. Thank you.